What do we do now? We're going to look at probabilities. Are there any other questions that you want me to respond to regarding the things that you have looked at, the videos that you looked at? I'm going to assume that that's been done. Okay, but I brought this up just so that there's a kind of a little bit of a review. But if there are other questions, I'd like to bring them. Yes.
A question on FF I think I got through and understood what was going on. The samples that you take, the futures, that's essentially just runs of FF replan. Is that what each of those are?
No, it's the futures are how the actions will behave. And then you give that, so in some sense you provide a deterministic domain. Okay, you're going to provide a deterministic planning domain. And then you're then going to ask FF to solve that deterministic planning problem. So what you are sampling are action outcomes. So you're saying each action, let's say a particular action had so a particular action has some precondition P, and it can either give E1 with probability 0.7, fx at E1 with probability 0.7, fx at E2 with probability 0.2, fx at E3 with probability 0.1. Then you're going to sample this action at that particular time point, okay, and then say, oh, okay, I'll just assume that this action at this time point will only give E2. So it became a deterministic action now. Notice that the same action at an earlier time point may have been sampled to be E1. This was this issue of common random versus non-common random numbers. Okay, the actions could essentially be having different different determinizations at the different time points. Okay, when you do this, you get a deterministic planning problem. And then that's not an easy problem to solve. It turns out that the entire deterministic planning community is about, given a bunch of deterministic actions, an initial state and a goal state, how do you come up with a plan fast? It's just that that problem is easier than the problem you're trying to solve. So you compiled your decision into that problem.
I'm still missing something. I'm missing because you said that these are outcomes, but then you said, well, I just picked E2.
Yeah, I sampled, yeah. So I sampled, so now if in this, so remember that at each time point, I have essentially for each action, I know what its deterministic version would be. Suppose I had two actions, A1 and A2. This is A1, and then there is an A2, which also said I'll take P2 and I'll give E1 dash with 0.8 probability, E2 dash with 0.2 probability. So here I would have sampled A1 as well as sampled A2. Similarly, here I would have sampled A1 and A2. Okay, now given this, then I have essentially, the simple scenario is assume that common random numbers. That means I have sampled A1 and A2, and they will have the same outcomes irrespective of the time epoch at which you are going to use them. Now, just because you have those actions doesn't mean that they're going to be part of your plan. Whether or not they're going to be part of the plan is what the planner is going to figure out. You have an initial state. Which set of actions are you going to string together to get to the goal state?
That's the part I'm missing. How do I get to the string of actions?
That's deterministic planning. That was done in 471. And in fact, I might very well spend some time here too. Okay, that's an easier problem, but those couple of you who are done 471 have known. It's basically it's like finding just a single graph path. That's fine. Okay, so if that's what you meant, yes, yeah. FF replan, yeah. FF replan is more than FF. I was just thinking in terms of FF. FF replan uses FF, and FF is a deterministic planner.
Okay.
If that's what you meant, then that's fine.
I think that's what I meant.
Okay.
What I was trying to figure out is how, because you're doing the sampling, you're using random numbers, which picks one of the outcomes.
Mm-hmm.
But then are you then from that outcome using FF to get to the
Exactly. So you get a deterministic planning problem. When you sample, you get a deterministic planning problem. Then you ask your friend deterministic planner to solve it
Okay.
and take the length of the plan it returns. It so happens that the complexity of that computation is NP complete. Okay, which looks nothing bad at all when we start talking about POM DPs in a second, because it's much worse there. Okay. Yes.
So in terms of replan with all outcomes determinization, when does replanning happen?
What do you mean, no, replanning happens always at the same time. Basically, FF replan, used all outcome determinization to figure out how to go from the current state to the goal state. So it made a long plan, and it's just going to do the first action in this long plan. So it will send the first action to the simulator. The simulator will then tell you what state actually happened. If that is the state that you expected it to happen according to your plan, then you would do the next action. Okay? If not, you want to replan. And one of the interesting things there is, suppose you made a long plan, and you did action A1, and you're expecting to get into some state S1. And then you sent A1 to the simulator, it said, no, you actually got into state S5. Now suppose S5 is actually in your plan, it's 15 steps down the line. You don't need to replan, you just skip over there and start executing from there. Okay, so there are such happy cases that can happen. But that's also considered replanning. It's just a degenerate form of replanning where your partial policy somehow covers what to do in that state. But a more general scenario is you look at the state that you get. If that state is not covered, then you start doing a plan from that state to the goal state. And in general, one of the interesting questions in replanning is actually what I just said, I'm going to remove this, is also questionable, right? Because so, FF replan, so you basically, you are in S0 and you came up with A1, S1, A2, S2, SG. You made this plan using the all outcome determinization. And then you decided, well, I'm going to just do action A1 because this is the best plan to go to SG under these approximations. So I'll do A1. And then I'll actually do A1 in the real world or the simulator. And A1 will tell me what state actually occurred. If that is the same state as S1, I'm done. Basically, I just do A2. If it is actually any of these states, I'm still done. I do the next action from after that state. If it's not any one of these states, suppose I wound up going into S59, which is not in any of these states, then I need to replan. Now the interesting question, of course, is what is the replanning? What am I supposed to do? The simplest idea is try to find a plan from here to here. That's not necessary. Just find a plan from here to the closest state on the current plan. That is also fine. That's what you do, right? I mean, when there's a detour, you're going on a highway to Los Angeles and there's a detour, then you don't necessarily then start trying. Actually, my stupid GPS does that. But most normal people are not supposed to do that. Normal people, when they get out of the highway, they try to get back to the highway as soon as possible and then move on from there. A stupid GPS, if it's not a particularly smart one, will try to find a huge number of curvy roads on the precipitous mountain tops that will take you on a completely different route to Los Angeles. That's what that would look like. Of course, then it does give you useful policy. So if I suddenly find myself on the top of Mount Whitney, how do I get to Los Angeles? This will tell me. Okay, but that's not what I probably wanted to know. Okay, but that's another issue about replanning. When you actually do replanning, you could improve. FF replan doesn't do this. It just does. Okay, I find myself at 59. I'll try to go to SG. And if you heard, I don't remember if I made you see the part where I discussed Andrei Kolobov's work. Did I ask you to? I mean, you're looking like I never asked you to do anything, so I have no idea. So if I did discuss Andrei Kolobov's work. Andrei Kolobov's work can be understood in terms of this, basically improving this deep planning abilities. Any other questions? Okay. So what I'm going to do now is quickly mention to you PALM-DP model and then make you read the probably the most interesting and did I start this already yet? Is it going on now? Yeah, it is going on. Okay. Most interesting algorithm you have to read in this class, which is value iteration for PALM-DP by the time you come to the next class, and then we'll discuss it a little. Okay. So in understanding PALM-DP, remember all this other stuff that we have done, and then keep asking yourself how does it connect. But I would make some connections, but others you should be able to see yourself. Shouldn't it go? Okay. Okay. So there are basically, I mentioned this already that when we were talking about MDPs, that if you're just predicting, then it's a Markov chain, and if you also have action choice, it's Markovation process. And similarly, if you have partially observable world, if you're doing prediction, you get hidden Markov models. And those of you who know HMMs know that they have a lot more uses than MMs, Markov chains, okay, MCs. And then planning is basically if you have action choice in the PALM-DP. Sorry, if you have action choice in your hidden Markov model, then it becomes a PALM-DP. So then you are trying to decide what is the best set of actions to do to reach a certain reward. Okay. So here is the PALM-DP model. Okay. So the idea is that you are essentially transitioning from S0 to S1 to S2, etc. The underlying system is transitioning that way. Okay. But unfortunately, you never will know. The agent will never know what the actual state it is in because the states are partially observable. Okay. Instead, every state, there are many ways of talking about, sensing. In fact, I mentioned sensing actions as if you actually do, sensing action is something that you do volitionally. That means you have to plan to do a sensing action. In PALM-DP, essentially, the simplest PALM-DP model, it essentially says that the moment you get into a state, it emits a particular observation. Do you see what I'm saying? Every time you go into a state, it emits a particular observation. So S0, it emitted an observation Z0, here Z1, here Z2, etc. Now, the interesting thing, of course, is you can make this into an MDP. How can you make this into an MDP? What? No. What should I do to Zi such that it will become an MDP rather than a PALM-DP? What?
You observe everything.
Yeah, but again, first of all, we are not talking at the state variable level. We are talking about state level. These are atomic models. Okay? So the ZRS. Okay? In fact, when you have that picture there, what you really have in the PALM-DP model, when you are providing the PALM-DP model, you provide essentially what's called the observation model. Okay? Remember, in MDPs, you provide the action model, right? What's an action model? Which is supposed to tell you, given that you are in S and you did an action A, what is the probability that you will get to state S dash? I have to give you these numbers. When I give you these numbers, that's considered the action model, right? If I do that, then basically I have given you action model. And then what other thing do you get in MDP? MDPs require this, MDPs also require reward model. The reward model essentially is depending on whether you're doing, essentially RSA. That's a slightly more general model. You can do R of S or R of SA. That means if you do an action A in state S, what is the reward you get? You're supposed to say this beforehand, right? Then it's supposed to come up with a policy of which action to do in what state. Okay, now this is what you need to specify an MDP. On top of it, you need to have to specify an observation model for PalmDB. What is the observation model? It tells you what is the probability that you would get an observation Zi when you are in state Si. That's it. Okay, so in general, what people would do is that the simplest model of PalmDB is you'll assume you have S1 to Sn states, and you have O1 to OK observations, and then it'll tell you basically, I mean, instead of O1 to OK or Z1 to Zk, whichever you want to call it. Okay, and I'm just supposed to, and the observation model tells you which observations are emitted by which states with what probability. Okay. Now, given that, what can I say about this observation model? What do I need to do it such that to it so that it will become an MDP? If it turns out, for example, think about it this way. Suppose k equal to n. That means there are exactly as many observations as there are states. And then P Zk given Si is equal to 1 if I equal to k, 0 else. Right? Is that correct? Okay, so if I'm in ith state, I will get Zi as my observation. Otherwise, I'll never get Zi as the observation. With one fell swoop, that's my observation model. And if I have that as the observation model, PalmDB becomes MDP. Keep that in mind, right? Right. And similarly, MDPs can become deterministic when essentially there is only one state for which the probability is 1, and for every other state, probability is 0. Okay, these are all generalized models. So whatever you do in PalmDB is more general than in MDP. Okay, so anyway, so what that means is that in general that doesn't have to be true. So a particular state can produce multiple different outcomes, depending upon its whim and wish. Okay, it might produce O1 sometimes, O5 some other times. And furthermore, two different states can produce O1 as the outcome. Which is why you don't know just from the observation which state you are in. Okay, observations give you partial information about the state you are. Okay, so that's fine, and then the observations do depend on the states, and based on that you do an action, and then if your model is a RAS model, that means you get a reward after doing an action in a state, then you get a reward. Okay, now these are graphical models. Basically, the idea is if there is an arrow to this, that means it's only affected by its immediate parents. So the reward is affected only by A and S0. Similarly, Z is only affected by S. So the first observation is only affected by the first state, not the action you're going to do in that state. Okay, right? And the action itself, this action that you did here, the first action you do has to be just dependent on the observation, nothing else. It can't depend on the state because it doesn't know the state. Okay, now things become more interesting. So obviously here you get, when you do action A0, in essence you did action A0 on S0. Right? Now notice that this can actually be a stochastic action. However, when you do the action, you get a specific state, S1. Right? If you're thinking there are multiple states possible, but when you actually do the action S0, you get a state S1. Now that state S1 depended only on the previous state and the action A0. Probabilistically dependent. Right? Okay? And then when you get to that state, you get an observation. That observation depends only on that state, not the previous state. observation you get depends only on the current state. Okay, and then you are going to do an action. Now, one of the interesting questions is actually, and then also that you get a reward. The reward depends on the action you do on the state you are in. The interesting question actually is, when you are picking the actions, what should the action depend on? When you're picking the actions, what should the actions depend on? I put some arrows there already. Sort of made up your mind. But the question is this reasonable? What did the action depend on in MDP? Current state, right? It depended on current state. But, so I can actually put a direct, interesting. I do have the previous observation. And I might as well, and I really should use the previous observation. Do you understand what I'm saying? And this is what makes this a non-Markov process. Do you see what I'm saying? Even though we call it POM-DP, partially observable Markov decision processes, it's not Markovian. For a Markovian decision process, the decision should depend only on the current something. Should depend only on the current something. And now we are saying it cannot depend on the current something. It has to depend on the history of the observations you have seen. So if I didn't tell you anything else, you should have to assume that you don't yet know how to compute the optimal policy for Markov decision process, right? However, you do know that it would have to depend on the full series of the observations. Okay, and what is interesting is, so this is the picture of MDP. This is a picture of MDP, and so, we had a picture like this for, this is a picture of MDP. We had a picture like this for MDP too. It's just that the MDP didn't have the Z variables. And the action only depended on the state directly. Here the action depends on all the observations that came before. Okay, can somebody give me a reason, a good example of why optimal action should take into account the history of observations? No, give me an example. Give me a telling example. I mean, obviously it's required. Just give me an example. What?
For a blind person who's observing the state, he should know that from his previous voice, he woke up, he would know where the surrounding is.
Mm-hmm.
Then when he reaches the gate, he would reaches the wall, he just senses it partially and understands that yes, this is the end of the road or this is the end of the house. And then,
so first of all, blind people have to be much smarter than us, right? Because they have to solve a POM-DP. We have to solve a POM-DP in our general life, but many cases we solve MDPs. Okay, blind people basically are looking at partially observable world, and that's the case. But tell me, when we are blind ourselves, we all deal with blindness. So that's true. Actually, that's a good example. But you can always say, oh, that's just for the blind people. We do MDPs. So we all have to deal with POM-DPs. So give me another example. I have one, but I'm trying to say, yes.
To use the old phrase, doing the same thing twice and expecting different results is the definition of insanity or something like that?
That's okay. So the question, actually, I do want to talk about that, by the way. I think I may have mentioned this in this class, but I want to talk about that. But before that, other examples. I don't quite know how that will connect. But what?
Medical observation.
Why?
Because you may come in and recognize one symptom, and then the next symptom might help you narrow down what it is based on the two observations rather than just one observation.
Yeah, that's true. How many of you drive? Right. Okay, why don't we just change lanes when there is nothing in the rear view mirror? There's nothing in the rear view mirror, so I must mean that there's nobody on the side of me. So I change lane, and then I get into an accident. I mean, I don't know about you, but every few hours of driving, I say, thank goodness I look like this. Because there will be this little car. You know, most cars somehow find themselves in the blind spot of some car. I don't know why this happens, but that's the case, right? Now, how do we avoid doing the inoptimal action of changing lanes? You would have to reason saying, yes, there was this little red car right behind me a while back. I didn't see it pass by me. The fact that I have no car right now doesn't necessarily mean there's no car. I have to take the sequence of observations into account. There are many such things. I mean, obviously, all the other ones the one that about the medicine, the one about blind people, that's all completely true. And in fact, we can all be made blind by essentially just, if we just put stuff on our, if we close our eyes and try to make sense, then we have to feel where we are going. And then based on, and that's, for example, there may be two doors, and you come to the door, you don't know which door you are at. Then you will realize if you, on the way to it, I touch something which look like a slide screen, then it must be this door. Whereas if not, then it must be that door. Because in this particular map, right, if I go to that door, I will probably touch this. If I go to that door, I'm not likely to touch that. So once again, I take the observations into account. Okay, life is PalmDP, by the way. In fact, all sorts of interesting things that you do make sense in terms of this partial observability. Most of what we wind up doing, sometimes one of the interesting things that PalmDPs do, and I mentioned this in the previous two videos, is if I have a belief state, which is S1 to Sn, and I need to get to a goal state, which is either S5 or S7, right? The question is, without knowing where I am, how do I get to those things? Now, I can do progress towards the goal state. I can also reduce the uncertainty in the current state. So, actions which only reduce the uncertainty in the current state can actually be quite relevant for planning. Do you see what I'm saying? Okay, that's what I was telling you earlier in terms of when you wake up in somebody's room and you need to find your way to the bathroom, you first find the wall. I don't expect that you needed the wall as the goal, but touching the wall helps you localize yourself. And from there, then you can make progress towards the goal. Okay, that's something that only makes sense because, in terms of partial observability. Such a plan can never be the right plan if you had full observability. Do you see what I'm saying? It can never be the optimal plan if you have full observability. Okay. Okay, so then that's your model. And so obviously, I don't need to go through this. This is sort of, basically singing the praises of the general MDP model, PalmDP model. And then there are lots of interesting examples of PalmDP. The one, from OR community, which I don't want to talk about right now, is the canonical example is this machine maintenance problem. I won't talk about it. In our case, robot navigation problem. So an example essentially in the robot navigation problem is I don't know which state I am in. So let me actually show you an example if I can get, and then I'll come back to this. I may have to go for a while. Okay, this one. Okay, so one of the interesting things is, okay, actually, well, I mean, we'll say in a minute, if not today, by next week, that essentially we would like to think in terms of belief states in the PalmDP. The idea is, even though the PalmDP, the policy has to depend on the history of observations, you can make it depend on just the current belief state. Where the current belief state is not the current state, but is the current distribution over the states. And it turns out that the belief state completely captures all you know up until that point. You see what I'm saying? And then your policy will then has to be just like MDP policy says, if you are in this state, do this action. For partially observable MDPs, you first go into the belief space belief state, space of belief states, and then think in terms of a policy is basically now going to say, if you are in this belief state, do this action. If this belief state, do this action. Now, of course, it looks very nice thing to say, but two huge problems, actually one really big huge problem, which is that the number of belief states is infinite. So there is no table large enough in the world to say if you have this particular distribution, do this action. If this particular distribution, do this action. In general, what would have to happen is that in this range of distributions, do this action. In this other range of distributions, do this action. So that's how actually POMDP value function would be over essentially ranges of belief states. It has to be. Okay. Now, one of the interesting things is if you think in terms of belief states, as you do actions, the belief state, that's what we were talking about earlier. As you do actions, your belief state changes. Okay. Now, as you do actions, the belief state can change in such a way that you have more certainty about where you are. It should not be surprising. So here is an example where this is our known the grid example, right? So suppose I started with essentially not knowing where I am. I'm definitely not here and not here and not here. But everywhere else I can be with equal probability. Okay, so I have a uniform distribution over 3 plus 2 plus 4, 9 states. So 1 over 9 is that number, 0.111. Okay, now if I want to localize myself, for example, if I do actions, as I do actions, the belief states change. Okay, so one idea is suppose I just blindly did left 5 times. Blindly did left 5 times. Okay, then the belief state I would get is this. And notice essentially because I have blindly moved left, most of the probability mass is now concentrated on the 3 leftmost cells. And there is much less probability mass left here. There's still some left because essentially just because you said you wanted to move left doesn't have to move left. You may go up or you may stay in the same place and all that stuff. Right? Okay. And similarly, if from here I blindly moved up, then I would get that. Okay. And if I'm 5 times up, and similarly right 5 times, I'll get that. It's again, this is mostly to show what, sort of give you a reason to believe your intuition that by doing action, you reduce uncertainty in this particular case. You have better idea of where you are right now. Okay, now this is also connected to this notion of cardinality. The belief state cardinality hasn't reduced. It's the same cardinality because there is no new cell that has become 0 after doing any of these actions, right? So that means they will still be in the belief state if you think in terms of the non-deterministic representation. But you can clearly see that these are more peaked distributions. Right? This one puts all its probability mass in these 3. This one puts all its probability mass in those, and this one puts all the probability mass in that lower one. So in some sense, it has lower entropy. Right? And by doing the actions, you actually, this particular set of actions, you reduce your uncertainty. Yes, there was some question. Yeah. What?
Doesn't the cardinality of the belief state change between A and B?
Why did it change? Because is anything become 0?
Yeah, bottom right corner.
No, those were always 0.
Bottom right corner.
Oh yeah, okay, fine. That's true. Good. That is true. In this case, you're right. In this case, you're right. So, but that was because of these particular actions. These actions models had the property that when you try to move in one direction, they'll only move in 2 other directions. So, if you were here and you made 5 lefts, okay, essentially, it's still pretty hard to believe that happened. It's like, it's not 0, it's like 10 power minus 7 or something. It's like for 3 digits it is 0, right? Because it becomes very close to 0, but it doesn't become. I mean, zeros are surprising, in probability distributions. I mean, those of you who know, for example, I mean, I don't know, some of you may have background in machine learning, for example, and this whole entire sparse learning idea is to come up with distributions which will actually drive down some possible relevance of some of the features to 0. Okay, it's not normal to find them actually. Okay, so I mean you're right, but I think in this case it's written as 0, but it's actually 10 power minus 7 or something, because even if you are here, it's actually possible, and if you went 5 times left, there is non-zero probability that you're still stuck there. Right? Remember, this is our normal actions for if you try to go left, then with 0.8 probability you will go here, and 0.1 you will go that side, 0.1 will go that side. And in those two, with 0.2 probability, you will essentially stay there. Right? So 0.2 power 5 is the value that should be there, actually.
0.1 power 5. The reason that you're negative.
Oh, yeah. 0.2 would have go up. Okay, I'm sorry. Yeah, 0.1 power 5. What? What? I understand. That's true. Times, yeah, exactly. So now the interesting thing that, I mean, we have to stop here, but the interesting thing that I'm going to make you read, and then we'll discuss next class, is you read the POMDP part of Russell and Norwig's chapter. Okay. The reason you will be reading is basically you will understand how to, in particular, compute. So basically, what I did here is this equation. Given an action and a belief state, what would be the new belief state after doing that action? Okay, and if I can compute that, then in essence, one of the interesting things is that I can compile the POMDP in the space of normal states into an MDP in the space of belief states. At which point I'll say I'm done. I don't need new algorithms for POMDPs. I have algorithms for MDPs. And then you laugh at me because I have algorithms for MDPs if the state space is discrete, which we thought we did not have to deal with. It's just discrete, and I understand we made an assumption, we'll move on. But then the moment you come here, you are going to be compiling, essentially, you're going to say POMDPs are nothing but MDPs in belief states. But then these belief states are continuous quantities. So you do need new kind of algorithms because the normal value iteration doesn't make sense. Okay, so we will talk about two kinds of ideas. One is, of course, we will try to, so this is basically a belief state MDP. We'll talk about this, and then we'll say, first we'll try to understand, before we even look for optimal algorithms, we'll try to understand how to do something like an approximate RTDP kind of algorithm for POMDP. Okay, and that in itself is interesting, and that is that picture. And then we'll also talk about how to, if you don't want to solve POMDP correctly, value function of the POMDP correctly, then you can try to solve approximations of POMDP. And there are two kinds of approximations. One is you assume nothing is observable, and the other is you assume everything is observable. And one way you will get upper bound, one you will get a lower bound of the value function. And you can use that to actually also do this kind of approximate POMDP analysis. And then finally, after doing that and staying away as much as possible from exact value function computation, we will actually look at the exact value function computation, and and then that's where you actually would have, it would be very helpful if you read the algorithm before coming to the class. Okay, that's what we'll do next. Yeah.
If I told you that I don't